Welcome to section 4.3, Exponential Functions. Objective 1, evaluate exponential functions. We've already seen how to interpret exponential expressions with rational exponents. For example, 2 to the fourth equals 2 times 2 times 2 times 2. 2 to the negative third equals 1 divided by 2 to the third. And 2 to the power 3/4 equals the fourth root of 2 thirds to the power 3. But what is the meaning of a to the power x, where a is a positive real number and the exponent x is an irrational number? A precise definition requires calculus, but we can use rational approximations to obtain approximations for exponential expressions involving irrational numbers. Most calculators either have an x to the power y key or a caret key for working with exponents. To evaluate expressions of the form a to the power x, we're going to first enter the base a and then press either key to enter the exponent x and then press the equal sign or enter. Okay. All right. In our first example, we're going to use our calculator now to evaluate powers of 3. So here's our calculator. So we're first going to evaluate 3 to the power 1.4. So I'll press 3 and then my caret, and then I'll enter in 1.4. And that equals 4.65553672. Okay, so we are going to enter that onto our screen. So this equals 4. I was about to write a 3. I don't know why. .6. Why did I write a 5? I got this. 655. Let's go to 4 decimals. Okay. Now let's evaluate the next one. So 3 to the power 1.441. Okay. Let's go to 4 decimals. So 4.7070. And then the next one, 3 caret 1.414. And we got 4.7277. Okay. And I'll scoot this over. And we'll take the next one, 3 caret 1.4142. All right, so that is 4.7287. And then the last one here, 3 caret square root 2. Enter. All right, 4.7288. Awesome. Okay. So it can be shown that the laws for rational exponents hold for real exponents. So the laws of exponents states that if S, T, A, and B are real numbers, A is greater than 0 and B is greater than 0, then you have the following rules. Now all of these rules are a part of the law of exponents. So if you have two bases that are the same and you're multiplying, you're going to add their exponents. If you have a base with a power raised to another power, you multiply the powers. If you have 2 bases multiplied together raised to a power, you can distribute the base or the power to the 2 different bases. 1 raised to a power is just 1. A base raised to a negative exponent requires you to move that base in power to the denominator and then changing the sign of the power to positive. And then base raised to 0 equals 1. So the definition for exponential function states that an exponential function is a function of the form f of x equals capital C a to the power x, where a is a positive real number, a meaning greater than 0, a does not equal 1, and capital C does not equal 0 is a real number. The domain of f is the set of all real numbers. The base a is the growth factor, and because f of 0 equals c a to the power 0, which equals c, c is called the initial value. Okay, so that is the basis for our exponential functions. So why is a equal to 1 excluded as a base? Okay, well, if we have f of x equals c a to the power x, and we gave a value of 1, okay, well, 1 to the power x, where x can be any value, we would get c. So f of x would equal c. So the function would simply be the constant function, which represents the constant function. So we want to exclude a from being, or a equaling 1 from being the base. Why can't a be negative? Okay, well, let's say we had, what number should we use? Let's do -2. So say our exponential function, we'll evaluate it at 1/2, where a is -2. Okay, and x can be any value, but I'm just choosing 1/2 to show you why a can't be negative. Okay, so we're just going to let c equal 1 in this case. And so we would get the -2 to the power 1/2. Okay, now this is the same thing as the square root of -2, okay, which is not a real number. Okay, so negative values are excluded from the values of a, because if we were to use negative values, then we have a high chance of getting a non-real number. Okay, so a has to be greater than 0, and it cannot equal 1, and a cannot be negative, which means it has to be greater than 0. Same thing. So, caution, it's important to distinguish a power function, g of x equals a times x to the power n, where n is greater than or equal to 2, an integer, from an exponential function, f of x equals c times a to the power x, where a is greater than 0. In a power function, the base is a variable and the exponent is a constant. In an exponential function, the base is a constant and the exponent is a variable. For example, f of x equals x to the 4th is a power function, and g of x equals 4 to the power x is an exponential function. Okay. So let's explore exponential functions a little bit. All right. So suppose we have the exponential function f of x equals 5 times 2 to the power x. Now we want to consider the ratio of successive outputs for a constant 1 unit increase in the input. Okay. So before we do, in your notes, if you can change this to f of 2 and this to f of 1, and then over here change this to f of 3 and this to f of 2. Okay, and this is 2. Let me make that polar a little. There we go. All right, so f of 1 would be 5 times 2 to the power 1, and then f of 0 would be 5 times 2 to the power 0. So we would get 10 over 5, which equals 2. Okay, f of 2 would be 5 times 2 to the power 2, and then 5 times 2 to the power 1. So in this case, we would get 20 over 5, over 10, 5 times 2, over 10, which equals 2. Then f of 3 would be 5 times 2 to the power 3, and then 5 times 2 to the power 2. Okay, so we would have 420 in the denominator, and then we would have 40 in the numerator, which would get us 2, and so on. So notice the ratio of consecutive outputs is the constant 2. So for an exponential function, f of x equals c times a to the power x, where a is greater than 0, a does not equal 1, and c does not equal 0, if x is any real number, then f of x plus 1 divided by f of x equals a, or f of x plus 1 equals a times f of x. Okay. All right. So we're going to now be working a little bit in identifying whether a set of ordered pairs is a linear or exponential function. So in this first example, we need to determine whether the given function is linear, exponential, or neither. And for those that are linear, find a linear function that models the data. And for those that are exponential, find an exponential function that models the data. Okay, so to do that, we are going to have to find the average rate of change between the points and then find the ratio of consecutive outputs. Okay, so let's first find the average rate of change. So let's first look at our first two sets. So these two. Okay. So to find the average rate of change, or in other words, the slope, we'll take the difference of the y divided by the difference of the x coordinates. And we would get negative 4 over 1, which equals negative 4. And then we'll do the same thing for the next two. So that would be negative 2 minus 2, and then 1 minus 0, which is negative 4 over 1, which equals negative 4. And then we'll do the same thing for the next two. So negative 6 minus negative 2 over 2 minus 1, which equals negative 4 over 1, which equals negative 4. And then for the last set, negative 10 minus negative 6, over 3 minus 2 equals negative 4 over 1, which equals 4. Okay, so notice that the average rate of change is negative 4. So now we want to find the ratio of consecutive outputs. So this is similar to what we did in a previous slide. So we'll first take f of 0 divided by f of 1, and that was 2 over 6. And this should be negative 1 because we're doing the first two. 0 and 1. 0 and negative 1, sorry. So that would be 2 and 6, which equals 1/3. Then we'll take f of 1 and f of 0. That's the next set of x coordinates, which would be negative 2 and 2, which equals negative 1. Then we will take f of 2 and f of 1, which equals negative 6 over negative 2, which equals 3. Then we will take f of 3 over f of 2, which equals negative 10 over negative 6, which simplifies to 5 over 3. Okay, so notice that the average rate of change for every 1 unit increase in x is negative 4. That's what we got here. Okay, thus, this represents a linear function where m equals negative 4. Okay, so m is going to equal negative 4, and our y-intercept is going to be the value when x equals 0. So that's this point right here. So b equals 2. So our equation will be negative 4x plus 2. Okay. Remember, in order for it to be an exponential function, the ratio of consecutive outputs will need to be a common constant. So we would get the same value between all of the ratios. In this case, we did not. So we would then look to see if it is a linear function, which it is. If we didn't have a constant rate of change, then it wouldn't be linear either. Okay, so let's do another one. All right, so here we have our points. So let's go through the process of finding the average rate of change. Okay, so we'll have 27 minus 81 divided by 0 minus negative 1, which equals negative 54, over 1, which equals negative 54. This one isn't looking like it's going to be linear, but maybe it'll prove me wrong. Next, 9 minus 27 divided by 1 minus 0, and that is negative 18 over 1, which equals negative 18. Nope, it's not. That's okay. But let's just continue. The average rate of change, 3 minus 9, and 2 minus 1. That equals negative 6 over 1, which equals negative 6. And then we have 1 minus 3 divided by 3 minus 2, which equals negative 6 over 1, which equals negative 6. So I know it's not going to be linear because my average rate of change between all of my ordered pairs is not the same. So let's see if it is an exponential function and all of my ratio of consecutive outputs should be the same constant value. So let's first start off with f of 0 divided by f of negative 1. So that's 27 over 81, which simplifies to 1/3. Then I'll take f of 1 over f of 0, which equals 9 over 27, which simplifies to 1/3. Okay. So now the next one is f of 2 over f of 1, which equals 3 over 9, which simplifies to 1/3. Okay, so this fourth one should also then equal 1/3 as well. Let's verify f of 3 over f of 2, and that equals literally 1/3. All right, so I have a constant of 1/3 for my ratios. So the average rate of change is not constant, so the function is not linear, and the ratio of consecutive outputs is a constant, 1/3. So that means the growth factor, A, is going to be 1/3, and the initial value, which is C, is going to be 27. So our function g of x is going to be 27 times 1/3 to the power x. Ooh, beautiful. All right, let's do one more. All righty. So let's find the average rate of change. So 7 minus 4 divided by 0 minus -1. So that would be 3 over 1, which equals 3. Next one, we have 11 minus 7 over 1 minus 0, which equals 4 over 1, which equals 4. Next, 16 minus 11 divided by 2 minus 1 equals 5 over 1, which equals 5. And the last one, 22 minus 16 divided by 3 minus 2 equals 6 over 1. Yep, 6 over 1, which equals 6. So my average rate of change values are not the same, so it's not linear. Now we do the ratios. So we'll start with f of 0 divided by f of -1, and the y's are 7 and 4. Then f of 1 over f of 0, and the y values are 11 and 7. Those can't simplify, so next we have f of 2 over f of 1, and that's 16 over 11. Okay, that can't simplify. And then f of 3 divided by f of 2, and that goes to 26 over 16, which can be simplified to divided by 2, 11 over 8. All right, so neither the average rate of change or the rate of consecutive outputs is constant. So that means we have a set of ordered pairs that is neither a linear nor exponential function. So this is not applicable for this set of ordered pairs. All right, graph exponential functions. So if we know how to graph an exponential function of the form f of x equals a to the power x, transformations can be used to obtain the graph of any exponential function. So here we have an example where we're asked to graph the exponential function f of x equals 3 to the power x. Okay, and so what I want us to do is to utilize our calculator to help us complete our table so that we can then graph our points. So let's grab our calculator. Alrighty. So I'm going to move this over here. And now we're going to go to y equals, and we're going to enter in our function, so 3 to the power x. And we're going to now enter that in and go to our table. So second graph. Okay. And so now we have some specific values that we want. So I do see some of my values on my calculator already. So let's enter that onto our table. So 0 is 1, 1 is 3, 2 is 9, 3 is 27, and 10 is 59,049. Okay, so now I want to go to my negative values. So I'll just move this up. Okay, so I have 1.7 e to the negative fifth. So that's a very, very small number. And then I have 3, negative 3 is 0.037, negative 2 is 0.1111, and negative 1 is 0.3333. Alrighty. Okay, so now I want to graph these points. Okay, so I'm going to take these points and place them on my graph. So I'm just going to estimate where these are. These are decimals, and some of them are very, very small. So as long as you get close to the area, you are okay. All right, so actually I'm going to wear my calculator here. Okay, so I can see my points. So I have 0, 1. So we're going to make that right here. And then 1, 3. And then 2, 9. 2, 9. And then 3, 27. And then 10 is like not even on my screen. So that's okay. And then everything else is much, much smaller. So just going to get closer and closer to 0 as we go. Then we can connect the dots. Alrighty. Okay. So now that we've graphed this function, let's answer some descriptions for this graph. So as x approaches negative infinity, right? So negative infinity, so it gets smaller and smaller. F of x is approaching 0. So it's getting closer and closer to the x-axis. As x is approaching infinity, so as x is getting bigger and bigger, f of x is going to infinity. So it's approaching infinity. It's getting larger. Okay? Our horizontal asymptote is y equals 0 because that's the line that our graph is approaching but never crosses. Our range is going to be from 0 to infinity. Okay? So our range, all of the y values are above the x-axis, but they never equal 0. F is an increasing function, and so F is 1 to 1. Okay. So the properties of the exponential function when a is greater than 1. Your domain is going to be the set of all real numbers, or from negative infinity to infinity using interval notation. The range is also the set of real numbers, but just the positive values, or from 0 to infinity using interval notation. There are no x-intercepts because it does not cross the x-axis, and the y-intercept is 1. The x-axis, y equals 0, is a horizontal asymptote of the graph of f as x approaches negative infinity. Now, our exponential function is an increasing function and is 1 to 1. The graph of f contains the points -1, 1 over a, 0, 1, and 1a. The graph of f is smooth, continuous, with no corners or gaps. So this is when you have an exponential function where a is greater than 1. So in our last example, our a was 3. Okay. So now in this example, we're asked to graph the exponential function f of x equals 1/3 x. Okay, so let's grab our calculator to help us complete our table. Okay. So we're going to go to y equals. I'm going to clear my previous function, and I'm now going to enter in 1/3 x. So I'll get my fraction, 1/3. And just to make sure that I enter it in correctly, I'm going to add a parentheses in the beginning here. I want it to look exactly like it does in my notes. Raised to the power x. Great. Okay, so I'm going to press enter. And now I'm going to go to my table in my calculator. So that's second graph. And I'm going to complete my table. So -10 is 59,049. -3 is 27. -2 is 9. -1 is 3. 0 is 1. Now I'm going to move this down a little bit so I can get my last two values. Oh, I have fractions. Okay. So 1 is 1/3. 2 is 1/9. 3 is 1 over 27. And let's go get 10. All right. Ooh, it's a very small number. So 1.7 e to the -5th. All righty. So now I'm going to take these values and plot them on my graph. I hope that you noticed as you are writing them down that these values are very similar to the last ones that we did, except for what the y values were for 0, 1, 2, 3, and 10. For 3 to the power x are now the y values for -1, -2, -3, and -10. All right. Okay. So we're going to plot some of these points. All right. So 0, 1, and then -1, 3, and -2, 9, and then -3, -20, and then 27, and then 10. Oh, that's right off the board, so can't do that one. And then we have 1 and 1/3, which is 0.3333, and then 2, it just keeps getting smaller and smaller. All right, so let's connect our dots here. There we go. Nice. All right, now that we have this graph, let's look at some of the demographics. So as x approaches -infinity, so as x is getting smaller and smaller, f of x is approaching infinity. As x approaches infinity, meaning it's getting larger and larger, f of x is approaching 0. The horizontal asymptote is going to be y equals 0, which is the x-axis. The range is going to be 0 to infinity. F is a decreasing function. Okay. X is a decreasing function, and so f is 1 to 1. Okay. So to summarize, when you have an exponential function where a is between 0 and 1. The domain is the set of all real numbers, or from negative infinity to infinity using interval notation. The range is the set of positive real numbers, or 0 to infinity using interval notation. There are no x-intercepts, and the y-intercept is 1. The x-axis, or y equals 0, is a horizontal asymptote of the graph of f as x is approaching infinity. Your exponential function is a decreasing function and is 1 to 1. The graph of f contains the points -1, 1 over a, 0, 1, and 1a. The graph of f is smooth and continuous with no corners or gaps. Okay. So it is worth noting that the graph of f of x equals 1/3 to the power x can be obtained from the graph of f of x equals 3 to the power x using transformations. Note that f of x equals 1/3 to the power x equals 3 to the power negative x. So the graph of this function can be obtained as follows. So in our first visual here, we have the graph y equals 3 to the power x. But if we replace x by negative x, then we are reflecting about the y-axis. So we reflect over the y-axis, which then gives us the graph 1/3 to the power x. Okay, so we use transformations to get between the two graphs. So now let's graph the exponential function f of x equals 3 to the power negative x plus 1 and determine the domain, range, and horizontal asymptote and y-intercept of f. So we're going to first start with the graph of y equals 3 to the power x from our previous example, which we have here. So now, to get to our function 3 to the negative x plus 1, we first are going to replace x by negative x. This then means that we're going to reflect about the y-axis. So all of the points that we see here, we are now going to reflect them over the y-axis. So 2, 9 is now -2, 9. So -2, 9. Okay. 1, 3 is now -1, 3. 0, 1 is now 0, 1 because it lies right on the y-axis, so it didn't actually move. Okay. And the point -1, 1/3 is now 1, 1/3. That's right here. Okay. And then we have -2, 1/9 is now 2, 1/9. So it's even smaller. All right. And so, let me actually touch the dot there. Let's redo that one. Alrighty. There we go. All right. Okay. So now that we have replaced our x with negative x, so this is the graph of y equals 3 to the negative x, we can now add on our 1. So we are going to add 1 to the y coordinate, which means we're going to shift up 1 unit. Okay, so all of the points that we graphed here, we're now going to shift them up 1. So our y value is going to increase by 1. Okay, so let's take our first point here, which is -2, 9. Well, let me label all of these for us. So this is going to be -1, 3. And this is 0, 1. This is 1, 1/3. And this one is 2 and 1/9. Okay, so all of the y coordinates are going to go up by 1. Okay. So we first had -2, 9. So now it's going to be -2, 10. So -2, 10. And then we had -1, 3. So now we're going to have -1, 4. We also had 0, 1. So now we're going to have 0, 2. We also had 1 and 1/3. So now we will have 1 and 1 and 1/3. 1 and 1 and 1/3. Okay. And we had 2 and 1/9. So now we'll have 2 and 1 and 1/9. I'll just put that down here. All right. And so now we can connect the dots. Okay. Awesome. And so now our horizontal asymptote also increased by 1. So it was the x-axis, but now it's y equals 1. Okay. So our domain is going to be all real numbers. Our range is going to be 1 to infinity. Our horizontal asymptote is y equals 1. And our y-intercept is 2. Okay. Alrighty. Objective 3, define the number e. So many problems that occur in nature require the use of an exponential function whose base is a certain irrational number symbolized by the letter e. The number e is defined as the number that the expression 1 plus 1 over n to the power n approaches as n approaches infinity. In calculus, this is expressed using limit notation as e equals the limit as n approaches infinity of 1 plus 1 over n to the power n. So the number e is an irrational number like pi. So we can use a table of values to determine a numeric approximation of the value of e by letting the value of n get larger. And so here we have our table. We have some n's. When we plug that n into 1 over n, we get our values. When we add 1, we get the next set of values, which then we can raise to the power n, which then gives us the values of e at a respective n. So based on the table, the value of e rounded to 5 decimal places is 2.71828. Okay. Confirm the approximate value of e by typing in e into your calculator. The exponential function f of x equals e to the x occurs so frequently in applications, it's often referred to as the exponential function. Most calculators have the key e to the power x or exponential of x, which can be used to approximate the exponential function for a given value of x. So it asks us to refer to the user manual of your calculator to determine what buttons you have. But on our TI calculator here, I do want to show you where the E is located. All right, so there are 2 locations where you can find E on your calculator. So this is the lowercase letter e. The first one is right above your division button, right here. In order to get there, you will have to press second and then the division button, and it will place E on your screen. Now, if you are working with like e to the power 4, or e to the power 12, and you want to power, you can then just press the caret button and type in your exponent. But something else that you could use is the second location for e, and that's right above here, above your natural log button, ln. Now to get there, you will press second and then the ln button, and this then produces an e with the exponent location already selected. So either method will get you the same answers. Like if I were to press in 12 and then press enter, you see here I get the same values. So either approach works. It's just dependent on what you're comfortable with and also what your problem says, but feel free to use any of those methods. Okay. All right, so now let's explore graphing with E. So since E is greater than 1, the graph of f of x equals e to the power x will have the same properties as the graph of an exponential function. So here we're asked to graph f of x equals e to the power x. So let's utilize our calculator to help us complete our table. Okay, so we're going to go to y equals. We'll clear what we had before. And we are going to enter in our function e to the power x. And then press enter. Then we'll go to our table. And we'll move our cursor up to the values that we need. And we will complete our table. So they started with -2 and they rounded to 2 decimal places. So we'll just keep that same format. So we'll have 0.37. Then for 0, we'll have 1. And then for 1, we'll have 2.72. And then for 2, we'll have 7.39. All right. So now let us graph our function. So for 2, we have 0. Oh, it's really small. That's okay. -1. And then 0, 1, 2.72, and 2, 7.39. All right, let's connect our dots. Okay, so based off of this graph, we can identify our range as 0 to infinity, and our horizontal asymptote as y equals 0 with a y-intercept of 1. Very similar to our exponential functions. Okay, and since it is similar, we can now apply transformations to help us get other representations of e. So we're asked to graph the exponential function f of x equals -e to the power x plus 2. Determine the domain, range, horizontal asymptote, and y-intercept of f. So the first thing we're going to do is we're going to start off with y equals e to the x. So this is the graph that we just graphed. And so now we're going to apply transformations in order to get our function f of x. So the first thing that we're going to do is we're going to multiply each y by -1, which tells us to reflect over the x-axis. Okay, so this will give us the function y equals -e to the power x. Okay, so now we'll start with each point and then just reflect. Again, some of these values are very, very small, which is okay. Just try and get as close as possible. All right, so we had the point 0, 1, and so now we're going to have the point 0, -1. Okay. Then we have the point 1e, and remember e is approximately 2.718. So Now we'll have the point 1 negative e. And then we had 2e squared, and e squared is approximately 7.39. So now we'll have 2 negative 7. Okay. And then we add negative 1 over e, which is going to be 0.37. So we'll have negative 1 negative 0.37. And then we had negative 2, which was 0.14. So we'll have negative 0.14. And then we can connect our dots. All right. Okay, that's our first transformation. So now we are going to replace x by x plus 2, which means we're going to shift left 2 units. So all of these points that we just plotted, we're going to now shift left 2 units. Okay, so now 2e squared is now going to be 0 e squared. And then 1 negative e is going to now be negative 1 negative e, and so on and so forth. So let's label those. We had 2 negative e squared. So now we'll have 0 negative e squared. Then we had 1 negative e. So now we'll have negative 1 negative e. That's approximately 2.72. Okay. Then we had 0 negative 1, which will now be 0 negative, we had 0 negative 1, and then we want to move to the left 2. So our x is now changing. So now it will be negative 2, 0. Sorry, negative 2, negative 1. Oh boy, so many numbers. I hope you don't get as twisted sometimes like I do. But if you do, that's okay. You just gotta check to make sure that it is correct. Okay, so we were at 0, negative 1. We have to move 2 to the left, 1, 2, which will get us negative 2, negative 1. So what's changing? The x coordinate is changing. The y coordinate still stays the same. All right, and then we have our 2 smaller values. So we will have negative 3, negative 0.37, so 37. And we will have, let me label that for you. That's 1 over e. And then we'll have negative 4 at negative 0.14. So negative 4, and that is negative 1 over e squared. And then we can plot our points. Oh boy, come on. Okay, I could have made that one a little better. But it's okay. We know the idea of the graph. So our domain here is negative infinity to infinity. Our range is negative infinity to 0. And our horizontal is still y equals 0. And our y-intercept is going to be e squared. Negative e squared. Yeah, that's right here. That's our y-intercept. Alrighty. Objective 4, solve exponential equations. So Equations involving the terms of the form a to the power x, where a is greater than 0, a does not equal 1, are referred to as exponential equations. Such equations can sometimes be solved by using the laws of exponents and the following property. If a to the power u equals a to the power v, then u equals v. That is, when two exponential expressions with the same base are equal, then their exponents are equal. For example, if 2 to the power x equals 2 to the power 3, then x equals 3. So for these examples, we are going to solve the exponential equation. Starting off with a, we have 2 to the power x minus 3 equals 64. So the first thing that we want to do is we want to determine how we can get the same base. Because if we have the same base, then we can set their powers equal to each other. Right now, the base of one side is 2 and the base of the other side is 64. Can I make one look like the other? Well, I can. 64 is the same thing as 2 to the 6th power. So if I rewrite 64 as 2 to the 6th power, I now have 2 to the power x minus 3 equals 2 to the 6th power. I have the same base, so according to my property, I can now set their exponents equal to each other. And then that allows me to solve for x, which is 9. Okay. B, 125 to the power x plus 2 equals 25 to the power 3x plus 4. Can I make one look like the other, or can I make the bases have a common base? Or can I make these values have a common base? So 125 is equivalent to 5 cubed, and 25 is equivalent to 5 squared. So now I can rewrite the bases, 125 and 25, with a base of 5. So I will have 5 cubed to the power x plus 2 equals 5 squared to the power 3x plus 4. Now, according to the law of exponents, it says if I have a base raised to a power and the expression is then raised to another power, I just multiply the bases. So this is equivalent to 5 to the power 3 times x plus 2 and 5 to the power 2 times 3x plus 4. So now I have a base and a power. Since my bases are the same, I can set my powers equal to each other. So 3 times x plus 2 equals 2 times 3x plus 4. Okay, and now I can solve for x. So I'll have 3x plus 6 equals 6x plus 8. When I get all of my x terms together and all my constant terms together, I'll have negative 3x equals 2. So x equals negative 2 over 3. Awesome. So now let's solve an exponential equation that involves e. Similar techniques as we did in the last two problems, but we now have a side of our equation that has multiple factors. Okay, so what we can do is we can simplify the right side a little bit more so that we can combine it into one factor or one term. So let's take e to the power x raised to the 5th power times 1 over e to the 6th power. Okay, so when you have a side of your equation that has multiple factors, you want to combine it into one factor using the law of exponents. So in our first factor here, we have a power raised to another power, which we know by the law of exponents, we can just multiply together. So that's going to be the same thing as e to the power 5x. Now 1 over e to the 6 is a ratio, and the specific law of exponent that gives me a ratio is negative exponents. So that's going to be equivalent to e to the negative 6. So I have a base times it's another base that is the same. So I have two bases that are the same. So since they are the same, according to the law of exponents, I'm going to add their powers together. So this is going to be the same thing as e to the power 5x plus negative 6, which is the same thing as negative 6 or minus 6. So in rewriting my equation, I'll have e to the negative x squared equals e to the power 5x minus 6. Okay. Since I have the same base on both sides, I can drop the bases, set the powers equal to each other. So negative x squared equals 5x minus 6. Oh man, I see an x squared here, so that means I'm dealing with a quadratic. Okay, so what I'm going to do is I'm going to get all of the terms on one side. So I'm going to have 0 equals x squared plus 5x minus 6. I now can factor this quadratic, so that's x plus 6 times x minus 1. I can set both of these factors equal to 0 in order to find my values of x. So I'll have x equals negative 6 and x equals 1. Okay, so those would be the solutions to my equation. Alrighty. All right, now we have a word problem involving exponential functions. So this word problem deals with exponential probability. So between 9 p.m. and 10 p.m., cars arrive at Burger King's drive-thru at the rate of 15 cars per hour. So that's 0.25 car per minute. The following formula from statistics can be used to determine the probability that a car will arrive within t minutes of 9 p.m. And that formula is f of t equals 1 minus e to the power negative 0.25 t. First, we are asked to determine the probability that a car will arrive within 5 minutes of 9 p.m. That is before 9:05 p.m. So to do that, we are going to let t equal 5 because t represents the minutes within or after 9 p.m. Right, within t minutes of 9 p.m. So after 9 p.m. So we are going to substitute in 5 into our formula. So I have 1 minus e to the power 0.25 times 5. When we evaluate this, and we will need our calculator to do so, we are going to get the following value. So let's quit out of our table. I'm going to clear my screen. I'm going to enter 1 minus e to the power negative 0.25 times 5. So just like I see it in my notes. And I get this expression. So 0.713495. Okay. So I want probability. You can leave probability as a lot of different representations, percentages, decimals. But in this case, we're going to write it as a percentage. Okay, so there is a 71% probability that a car will arrive within 5 minutes. All right, because remember the formula gives us the probability that a car will arrive within 3 minutes of 9 o'clock. All righty, let's do the next one. Now we want to determine the probability that a car will arrive within 30 minutes of 9 p.m. So now t equals 30. So we're going to evaluate our formula when t equals 30. So we'll substitute in 30 into our formula. And then we will use our calculator to evaluate. Okay, so I'm going to enter in exactly like I see it. So 1 minus e to the power negative 0.25 times 30. Enter. And I get 0.999447. So this means that there is a 99.94% probability that a car will arrive within 30 minutes. Alrighty, fun stuff. All right, now it wants us to graph f. Use a graphing utility with the following window settings to graph the function. So f of t equals 1 minus e to the power negative 0.25 t. Okay, so let's graph that function. Okay, so we'll go to y equals, clear this, and then enter in our function. So 1 minus e to the power negative 0.25 t, so that's x, and press enter. And we want to set our window to match what's here on the screen. So our x min is 0, our max is 30, our scale is 5, our y min is 0, our max is 1.1, our y scale is 0.2, our x is 1, and then everything else is already matched. Okay, so now let's graph. Ooh, okay, so let's see what our last question says. What does f approach as t increases without bound in the positive direction? So what does f approach? So f represents our y. As t increases, so t is our x without bound in the positive direction. Okay, so what does f approach? So f is going to be approaching what value? So let's trace. Let's see what's happening here. So our y is getting closer and closer to what value? Ooh, it's getting closer and closer to 1. It's getting closer and closer to 1. So as t increases, without bond in the positive direction, in other words, as t approaches infinity, f approaches 1. So f of t approaches 1. All right. So as t increases, the probability that a car will arrive increases. So it's getting closer and closer to that 100%. Okay. All right. And that concludes section 4.3.